video is about ratios and proportions related to inhalation therapy. Inhalation therapy is used by respiratory therapists working with people who have lung disorders. Part of their job is to analyze concentration of oxygen in the patient's blood, along with the carbon dioxide levels. We think of the lungs and the diaphragm and how they act as a pump to move air in and out of your lungs. The variables involved are the volume, the amount of air in your lungs, the pressure, whether it's applied by the diaphragm or say your rib cage around your lungs, increase the pressure, and the temperature affects the other two. If you think of the bike pump, how you have a cylinder with a plunger that goes up and down, and as you push the plunger down, the pressure increases and the volume decreases. And vice versa, when you pull the plunger up, the pressure decreases on the cylinder and the volume increases. Now, if you're pumping up a tire and you've been doing it a while, if you feel that cylinder after a few minutes, you will find that the temperature has gotten hotter. And that's how the temperature is related to pressure and volume. And we'll see that when we get to the formula, which is a combination of formulas generated by Charles and another gentleman named Boyle. And what we did was we combined those formulas to allow us to have one formula that involved all three variables. So here's our formula, and we have that pressure times volume divided by temperature equals the changed pressure, the changed volume, those multiplied together, divided by the new temperature. The important thing about this formula is temperatures must be in Kelvin units. There is a conversion number where 0 degrees Celsius equals a certain temperature in Kelvin units. Well, that temperature happens to be 273.15 degrees Kelvin. So this is how we convert from temperature in Celsius to temperature in Kelvin units. It's a linear conversion, so all we have to do is add that value. The key is you have to remember to do it. Let's take a look at an example of a problem using that formula. So this is example 1. If you have 250 milliliters of oxygen at a pressure of 1200 millimeters of mercury, what would the volume be if the pressure were changed to 200 millimeters of mercury? So the pressure is decreasing. That means if you think about your bike pump, the volume should be increasing. It doesn't say anything about temperature, so we're to assume temperature is constant. We're going to use that formula, but the nice thing about this example is temperature is constant, so that means the denominators are the same, so the numerators have to be the same. So this is the sort of simplified formula we get to work with. So now I'm going to pick out the values given to me. Here they are listed from the original problem. So I know everything on the left-hand side. I know the P2, the new pressure. I have to find the new volume. I'm going to substitute those in, and I have 1200 times 250 equals 200 times V sub 2. So I'm going to solve for V2. Well, I want to get rid of that 200 multiplied by V2. So I divide both sides by 200, and I punch that into my calculator, and I end up with 1500 milliliters for the volume after the pressure was changed. Let's take a look at another example. In this example, the pressure on a confined gas started out as 285 millimeters of mercury, at which point the temperature of the gas was 22 degrees Celsius. If the pressure were to be changed to 315 millimeters of mercury, what could the Celsius temperature be then? The pressure is being increased, so we're putting more pressure on that volume. What do you think is going to happen to the temperature? Do you think it'll go up or go down? Well, let's see what happens. Do you see any mention of the volume in this problem? No, volume is assumed to be constant since it's not mentioned. So that means these two variables are the same, so my simplified formula becomes this. So that might give you a better idea as to whether you think the temperature is going to go up or go down. We have these values from the original problem. I'm all ready to substitute them into my simplified formula, except I need Kelvin. So I have to take this T sub 1 and convert it to Kelvin. We do that by adding 273.15. So I end up with a new temperature in Kelvin. So I'm ready to substitute into that simplified formula, and here's what I get. I've got 285, my original pressure, divided by my temperature converted to Kelvin was 22 degrees Celsius. And then my new pressure, which was 315, and my temperature that I'm looking for. Now I have to solve for T2. What I do in instances like this is I'm going to cross multiply. So when I cross multiply, I see this. I have 315 times the denominator on the other side, and 285 times T2. So I'm still trying to solve for T2, so I'm going to divide both sides by 285. So here's what I have to plug into my calculator, and I come out with 326.22 degrees Kelvin. But I need Celsius. So now I have to use that 273.15, but I'm not going to add it this time. I want to go back to Celsius. I'm going to subtract it. Subtract the 273.15 from the 326.22, and I end up with 53.07 degrees Celsius. So did it go up like you thought? Because here, the ratio, if one goes up, the other has to go up also for these two to remain the same. So our original problem had the Celsius rounded to the nearest tenth. So we need to round this to one decimal place, the nearest tenth. So our answer is 53.1 degrees Celsius. That's the second example. Now, what happens if none of the variables are held constant? Here's the last example we're going to look at. A volume of 425 milliliters of oxygen is at a temperature of 15 degrees Celsius and a pressure of 125 millimeters of mercury. If the volume is increased to 475 milliliters and the temperature decreased to 12 degrees Celsius, what would the pressure be then? Every variable is accounted for in this problem. We need to work with the original formula, and we have to remember temperature in Kelvin. So I have to convert each of these temperatures to Kelvin. So let's start there. I'm going to take each of those temperatures, the 15 and the 12, add 273.15. So this gives me my new temperatures in Kelvin. So now I need to find P1V1 and P2V2. So I go back to the original and I find each of them. There's V1 and P1. Here's V2. I'm looking for P2. So that leaves me this list. So now I'm going to go ahead and substitute that into my original formula using the variable P2, because that's what I'm trying to solve for, and I end up with this equation. Let's get rid of this value in the denominator first, and we're going to multiply both sides by 285.15. and these will cancel. I still have 475 times my P2, and I need to solve for P2. Well, I need to get rid of this 475 multiplied by, so I divide both sides by 475. Over here, I've got a lot of stuff going on. I know that if I divide by a value, it's the same as multiplying by 1 over the same value. So that way I get this in the denominator where it needs to be. So here I end up with 110.67 millimeters of mercury. My original Celsius was rounded to the nearest tenth, so I need to round this problem also. So my final answer is 110.7 millimeters of mercury. This concludes the video.